can we use rulers and marbles to better understand what Kepler's second law is all about and why it's so important in understanding real orbits in the solar system? Real orbits aren't circles, they're ellipses. And when we have an ellipse, every ellipse has got two foci. For an object orbiting the Sun is at one of these foci. And Kepler's second law says that a planet orbiting the Sun will sweep out equal areas in equal amounts of time. What does that mean and what does it look like? And what we have is a certain number of marbles. And now, if I arrange both of my rulers so that they are meeting at one of the foci, this is where the Sun would be, we can see that with a fixed number of marbles, we've got a fixed area. Now remember, Kepler's second law says that as an object goes around the Sun, it will sweep out equal areas in equal amounts of time. So let's imagine that we have our object and it's out here and it's moving from here to here. In a certain time interval, this is the area that it will sweep out, and this is the distance that it'll travel in that time. What's going to happen as it proceeds around the ellipse? I make a mark here, and now I'm going to move my rulers around, keeping the marbles within the ellipse, so that once again, the area I've got here is exactly the same as the area that I had up here. So when our object is furthest from the Sun in its orbit, a place that we call aphelion, we can see that Kepler's second law, sweeping out equal areas and equal times, means that it's only covering a small distance in a certain amount of time. It's got a very low velocity. But as it carries on in its orbit, getting closer to the Sun, we can see that for the equal areas rule, we're covering a much longer distance in the same amount of time. Its velocity is increasing. And as it reaches its closest distance to the Sun, what we call perihelion, this difference in the amount of distance it's covering in a certain amount of time is massive compared to when it's at aphelion. This is why comets, as they come into the inner solar system towards the Sun, have a velocity that increases dramatically, and as they swing around the Sun, once again they slow down until when they're at aphelion, at their furthest point from the Sun, they are crawling around their orbits at a very low velocity. This application of Kepler's second law works for all orbits. So whether or not we have satellites orbiting the Earth, or we have a mission like the Rosetta mission, rendezvousing with comet Churyumov-Gerasimenko, understanding the implications of how the velocity will change is absolutely critical if the mission is to be a success.